Yellowstone National Park is one of the most beautiful places in all of the United States. It has geysers, hot springs, and canyons that are all caused by the supervolcano beneath it. This supervolcano is responsible for 3 of the largest eruptions in Earth's history, and it may be due for its next big eruption soon. The Yellowstone Supervolcano isn't your average volcano. It has been responsible for some of the most powerful eruptions on Earth, but not in a very long time. That makes it a bit more unpredictable than other volcanoes. In order to better understand what makes this volcano so special, we need to take a look at how volcanoes work and how they're measured. Volcanoes come in different shapes and sizes, but they all share one thing in common. They are built from magma that comes up from deep within the Earth. Magma is made when rock deep in the Earth melts into a hot liquid. When this liquid rock starts to rise toward the surface, it can collect in chambers beneath the Earth's crust, eventually forcing its way up through the crust and creating the volcano we see on the surface. Scientists measure a volcano's size by its height above the surrounding terrain and by the volume of its magma chamber. The larger the magma chamber, the more magma there is available to fuel an eruption. Volcanoes are also categorized by their shape, which is determined by the magma's viscosity or resistance to flow. Low viscosity magma is runny and creates broad, gently sloping sides like a shield volcano. High viscosity magma is thick and sticky and creates steep-sided volcanoes like a stratovolcano. Now let's talk about the explosive power of volcanoes. Volcanic eruptions are measured using the Volcanic Explosivity Index, or the VEI. This index takes into account factors such as the height of the eruption column, the volume of material ejected, and the duration of the eruption. The VEI ranges from 1 to 8, with 8 being the most explosive. Let's apply this knowledge to our favorite supervolcano. The Yellowstone Supervolcano is actually a caldera. A caldera is a large crater formed by the collapse of a volcano after a massive eruption. What makes Yellowstone special is the size of its magma chamber. It's so big that even if it were completely empty, its next eruption would be super colossal. So how do scientists figure out how much magma is left in the chamber? Well, it's not easy. Scientists use a variety of methods to estimate the amount of magma in the chamber, such as measuring the elevation changes in the land surface, observing changes in the patterns of earthquakes in the region, and studying the chemical composition of gases released from the park's geothermal features. These methods provide valuable insights into the dynamics of the magma chamber, helping scientists better understand the volcano's behavior and potential hazards. Now let's get back to the science. As of right now, the Yellowstone Supervolcano is in an inter-eruption period. The last major eruption happened 640 years ago. During this time, the magma chamber is slowly filling back up with magma. How full is it right now? Well, that's a tough question to answer. Estimates vary depending on who you ask and what methods they use. But most scientists agree that the magma chamber is somewhere between 20 and 90% full. How do they know that? Well, they've studied past eruptions and created models of the magma chamber based on their findings. For example, they know that the largest historical eruption at Yellowstone was the Lava Creek eruption in the year 639,000 years BC. This eruption had a VEI of 8 and ejected an estimated 2,500 cubic kilometers of ash and pumice. Using this information, scientists can create models of the magma chamber and try to match the observed features of the present-day caldera with the model. This helps them estimate how much magma must be present to reproduce the observed features. But there is another way to figure out how much magma is in the chamber, and it involves looking at the chemistry of the magma. Different magma compositions have different densities. This means that the density of the magma chamber could tell us how much magma is in there. To measure the density of the magma chamber, scientists use a technique called gravity and magnetic inversion. This involves measuring variations in gravity and magnetic fields over the area. These variations can then be inverted to create a 3D model of the subsurface density variations. This model can help identify areas with high density, which may indicate the presence of dense magma. However, this method has its limitations because it cannot distinguish between different magma compositions. So while scientists can identify areas with dense magma, they may not be able to determine the exact composition of that magma. Understanding the magma's composition is important for assessing the potential explosivity of future eruptions, because different compositions have different eruption styles and hazards. Despite these challenges, scientists continue to refine their models and techniques to improve our understanding of the Yellowstone Supervolcano and its potential risks. Recent studies have provided new insights into the magma chamber beneath the Yellowstone Supervolcano. Using advanced imaging techniques, scientists have discovered a vast network of interconnected magma reservoirs beneath the caldera. This discovery suggests that the magma chamber is more complex than previously thought, and that the magma supply system is more extensive than expected. One of the key findings of the study is the identification of multiple magma lenses at various depths beneath the caldera. These lenses range in size from a few to several hundred square kilometers and are interconnected, forming a network that extends over a large area. The researchers believe that these lenses represent different stages in the evolution of the magma chamber. The shallower lenses may contain more evolved magma that is less likely to erupt, while the deeper lenses may contain more primitive magma that is more likely to erupt. Another important finding of the study is the identification of a low-viscosity magma pathway that connects the deep magma sources to the shallow magma chambers. This pathway allows for the efficient transfer of magma from the deep reservoir to the shallower chambers, where it can accumulate and eventually erupt. Understanding the structure and dynamics of the magma chamber is crucial for assessing the risk of future eruptions at Yellowstone. The new imaging techniques used in this study provide a detailed view of the subsurface, allowing scientists to better understand the processes that drive magma ascent and eruption. In addition to the new imaging techniques, scientists are also using other methods to study the Yellowstone Supervolcano, such as seismic tomography. This technique involves recording the travel times of seismic waves as they pass through the Earth's crust. By analyzing the variations in travel time, scientists can create 3D images of the subsurface and study the structure and composition of the magma chamber. Another method used by scientists is known as geodetic monitoring. This involves measuring changes in the Earth's surface using instruments such as GPS and satellite radar. These measurements can detect even the smallest changes in the shape of the caldera, providing valuable insights into the movement of magma within the chamber. These new discoveries and research methods are helping scientists to create more accurate models of the Yellowstone Supervolcano and improve our understanding of its behavior. This knowledge is essential for assessing the risk of future eruptions and developing effective monitoring and response strategies. If you're enjoying this video, make sure to subscribe so you never miss any of our latest content. We explore the most fascinating topics in science, technology, and nature. As for when the next eruption will happen, scientists are still working on that question. Some say it could happen in the next 100 years, while others say it won't happen for thousands of years. It is worth noting that volcanic eruptions are extremely complex geological events influenced by various factors such as magma viscosity, gas content, and tectonic setting. Predicting the exact timing of an eruption is challenging and often inaccurate. While scientists strive to improve their understanding and monitoring of volcanoes, the unpredictability of these natural phenomena remains a significant challenge. What do you think? Will the next 100 years be the time of the next super eruption at Yellowstone National Park, or will it be thousands of years from now? Let us know your thoughts, and don't forget to subscribe for more videos like this one. Thank you for watching.